So today I want to revisit the concept of average case running time. We started talking about this in the last set of video lectures. If you haven't watched those, please at least go watch the last one or two to make sure that you're kind of up to speed on the discussion here. I'll review some of the concepts and then we'll do some actual analysis. But make sure that you are familiar with the things I'm talking about kind of before you dive into this set of videos. So we'll talk about average case, do some analysis, and then if there's time, I'll introduce some canonical problems that we'll be looking at throughout the rest of the course. So I want to talk about how do we understand average case running time, and to do that, I want to introduce a few different concepts. So first, I'll say T of A is the running time of our algorithm on input A. Right? So if I plug an array into this T of A, that gives me our running time. So here we're looking at the algorithm unique elements, right? So again, check the last videos for the definition here. But what unique elements does is it compares all pairs of elements, and if it finds any repetitions in an array, it returns false. And if it finds no repetitions, right? So every element in the array is unique, then it returns true. Okay, and we found that it has a quadratic worst case running time, but a constant time best case running time. So the question is, what's the average case? And the short answer is it's not just the average of the two, right? So we have to be more nuanced. So to understand this, we have to be able to write down what is the time it takes on input A, then what is the set of all possible inputs, right? So that's this script A of n is the set of all n element arrays. Absolutely massive set, right? Way too large for us to write down. P sub A is the probability that input A, that array A is the input to the algorithm. And then our average case running time is this, right? We sum over all possible inputs the running time of that input times the probability of that input. And that gives us the expected value of the running time given with the statistics we know about the inputs. So what are the problems? Well, one immediate problem is we can't possibly enumerate all of the arrays, right? There are too many of them. That's going to be typical for any algorithmic problem. You know, the space of inputs is typically absolutely massive, right? There are infinitely many inputs, which makes it difficult. In this case, there aren't infinitely many, but at least there are at least factorially many, probably more than that, probably many more than that. And then so if we can't enumerate them, how do we evaluate the sum, right? And then the second question is, where do those probabilities come from, right? Where do our statistics about the possible inputs come from? Well, so one possibility is that they come from experiments, that we actually just discover them empirically. But another possibility is that we think about the problem and we say, what would we expect to find, right, in these statistics? What kinds of inputs do we expect to see? And then let's do the analysis for this kind of input. So for example, with arrays, it's fairly common to say, let's just assume that the array is a random selection of elements from some universe, and then go from there. Okay, and we'll take a couple different approaches to these assumptions here. So real quick, before I go too much further, I want to make sure that it's clear that we can actually use the notation I've defined above to define worst case and best case, and it's quite simple. So here's my little aside. I can define the worst case of an algorithm, the worst case running time of an algorithm in terms of what's above by just discarding the probabilities and saying, let me look at the maximum over all possible inputs, right? The max over every element of this set of all possible inputs of the running time of that algorithm. Okay, that's worst case. That's the definition of worst case. Just search through all of the possible inputs and plug the worst one in. Right, that's what worst case means. And then the best case is analogous. So best case as a function of n is now the min of all A in the set n of the running time of input A. And if I want to be very precise and there are infinitely many inputs, it may be that I need to actually use a supremum here and an infimum here. And for those of you who don't know sup and inf, go look them up. They're kind of fancy maxes and mins, but sometimes, to be very precise, that's what I would need here. All right, aside is finished. Right there's my aside. So let's think about what kinds of properties of inputs we might expect to find. Okay, so let's make some assumptions about our inputs. All right, so suppose the set of possible array elements is very large. Okay, so here's one assumption we can make, is that the things that could be in our array are very, very diverse, right? So the set of possible array elements is huge, right? So assumption number one is set of array elements is huge, right? So like all double integers or something like that, right? That's a huge number of different things that could be in our arrays. And so, what would this mean? This might mean that a very significant portion of the arrays we test actually do have unique elements, right? So what might this suggest? And this is the actual assumption we're going to use. This might suggest that it's very unlikely that we'll find repeated elements in an array. Okay, so this means that most arrays return true. Right? Most arrays have unique elements. In other words, it's very unlikely to have a repetition in an array. Okay, so here's our assumption number one. So let's define PU as the probability that we get an array that has unique elements. Right? So this is the probability of array having unique elements or returning true, of array returning true, right? And the U stands for unique, right? So this is unique. So the probability that there are no repetitions in the array. What do we know about this kind of input? We know that this kind of input is an n-squared input, right? So the running time here, so t of n, I'll say t of a for unique element array is what? It's 1/2 n, make sure I get this right, n squared minus n. Right? And we worked that out in the previous set of videos. Okay. So there we go. So now we have some of this. We have some of this. So with probability PU, we have that running time. Okay. Because we're making this assumption that most of that we have a massive number of array elements. All right, 2, let's suppose that there's some fraction of inputs that terminate in linear time. I'm not going to try to characterize what these inputs look like, right? You're welcome to do that yourself. But for example, an input that takes linear time is one where the first element is equal to the last element. So we'll say that some of our inputs do this. Some of our inputs take linear time, right? Some inputs take theta n time. All right, and so this is linear time. I'm going to say that the probability of getting an input that takes linear time is PL. So PL is the probability of T of A equals n minus 1. Right. So this is, essentially we're modeling this as the input has the same element at the beginning and at the end. Right. A0 equals a n minus 1. Okay. And notice I'm leaving this symbolic. So PU, I haven't plugged in numbers for PU. PL, I haven't plugged in numbers for PL. And then PC, we'll have our third assumption be that some fraction of inputs, right? Some fraction of inputs have this constant time property, where basically the first two elements are equal. Some inputs have A0 equal to A1, which means they terminate in constant time. So PC is the probability of some input having a constant running time, right? And so this is what you would get if A0 equals A1 or A0 equals A2, or you find repetitions very, very early in the array. All right, so given all this stuff, what would we expect to see in terms of the running time? And how can we characterize the running time as a function of these different probabilities, right? That's the question that we'll be addressing next.